Okay, so welcome back. I hope you had a nice long weekend. I did extend the assignment because I was understanding that you guys were pretty swamped with stuff. So I extended it, but now all of a sudden it's the due date again. One thing that I want to say is this assignment probably feels like you're being thrown in the deep end, and I understand that. And that was sort of on purpose. I know, rude. But the reason that I'm doing that is, well, I mean, at the end of the day, it's what's expected of you when you leave this program, but we're not done the program, so that doesn't make sense. But the reason that I did that is because I want to see what you come up with. Okay, so as long as you're, putting your best foot forward and you're trying and you're, trying to figure out how to do this, even though it feels really, really hard, I just want to see what you come up with. Okay, and then that'll give me a good idea of where we're starting at, right? And so here, what I want to say is, well, how can I summarize that? This assignment will feel difficult, probably. Right, I'll just go ahead and say it as definitively. This assignment will feel difficult, but try your best, right? So that I can get an idea of where we're starting from. But try your best so that I can get an idea of where we are starting from. And maybe I shouldn't end with an exclamation mark. How about just a period? Fact. Where we're starting from.
And okay for the period.
Yeah. Where we're starting from. Okay, so if you're feeling like, what am I supposed to do here, right? Just do your best and try to put something together, right? You've got those questions to help guide you through, and really, I don't want you to feel like you have to go beyond those questions. If it's submitted after midnight, how much of a percentage of their grade will be deducted? I guess I haven't thought about it too much. Probably 10% per day is kind of a go-to deduction. Feels pretty harsh. But if you're working with deadlines, I guess that's just how it is. So let's say late penalty, 10% per day. All right. So like I said, it will take time to make this report, definitely. But this is our first one, right? I'm not expecting miracles to happen here. I'm really just using this to see where we're starting at. Go from there. Okay. All right. So I also posted, I know you don't want to hear it, a chapter 4 assignment. Chapter 4 wasn't really on anything analytical. It was on probabilities. right? And so I gave you the data set so that you can bring it into R, but there's no real analytics that need to be done. Oh, and what I wanted to say here, the first assignment that you're working on for tonight, I'll go really easy on you, okay? And then what I'm gonna do is I'm gonna post a version of the solutions, right? And so what I want you to remember is that there's no right or wrong way to write this report. There's no one way to write this report. In fact, there are an infinite number of ways because we would each approach the report in kind of a different manner, okay? And so what I'm gonna post once everyone's submitted is I'll post my version, okay? And then I might refer you to that, right? If I'm reading yours and I say, oh, okay, this part was kind of lacking, have a look at what I did, and maybe that's a good starting point for you, okay? And so I'm here to teach you, okay? And so I think the best way to do that is you give me what you've got, and then I'll see what I can contribute from there. Okay, and so I will post, they're not solutions, they're one version of what you might give me, okay? And so you'll have that to look back to for future reports. Okay?
Question.
Yes.
The assignment says that for part one, we have to have it nicely formatted. I don't know anything about like formatting, word processing formatting in RStudio is like a completely different animal. Should I be afraid? Because I don't really understand how that works.
No, because we're just using Markdown, I'm not expecting anything crazy. Just, simple paragraphs, bullets, maybe if they're useful. Yeah, the formatting is more like include graphs as appropriate and things like that. So yeah, don't worry too much about the formatting. You really can't go wrong with Markdown. It's pretty basic. It's like paragraph.
You would be surprised what I can do all with. I'm good at that.
Well, I'm very curious to see what you guys come up with.
I will appease your curiosity.
But yeah, so this one, just give me what you got. We'll go from there. Okay, I'm not going to mark it hard, but I do expect you to give me everything you've got. Show off a little bit. Doesn't feel like it. Okay, so yes, it is a hard assignment. It's a weird assignment. There are no rules, really, besides making part one and part two, which are the same, right? Except part two is where you show me exactly what you did. And in part two, you can be very, you can talk to me as the grader. Here's what I did here because, and my reasoning was because of this, right? Usually you would start with part two, right? You would write part two first, you would do your analyses, you would kind of talk around it, and then you would build your blurbs, kind of your paragraphs for the client after that. Okay? So that would be, I guess, my one piece of advice out of many pieces, I guess, is to start with part two. Okay? I'll even write it down. If you are having a hard time with the assignment, it might be easier to start with part 2. Then build part 1 from there. Good. All right. So, okay. Everyone's still feeling confused. That's okay. Just remember, I'm going to go easy on you, and we're just going to use this as a building block. Okay. It's going to let me tell you what pieces are missing. Okay. So, question?
Yeah.
Yes.
Question. So with this, can we start on can I start first on part 2, then build on part 1? Or can I just submit my part 2 first, then I can submit to follow the part 1 of the report? Or it should be part 1 first?
No, you can submit either part in whichever order you want.
Okay.
Yeah.
Thank you.
Yeah, that's fine. Okay. I suspect there will be a lot of Googling in your guys' future. How do I do this? How can I do this? What are my options for this? Right. And don't forget about that R for data science textbook, right? Even though we've only gone through some of the basics, right? You can still work through it, right? And read, yeah, and there's always YouTube if you like watching videos. What I'm finding is that I don't really like videos, which is so weird because I post videos of my own. Yeah. So yeah, in general, you should argue that they have an approximately normal distribution, unless they're very, very obviously skewed, then we can't. Then we would say that they're skewed. Yeah, good. Yeah. I started watching, there's this girl who does these, I guess she's a data scientist on YouTube, and she just posts videos on what it's like to be a data scientist. They're pretty fun. Oh, yeah, that's school, right? Busy, 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 busy. All the profs feel like they're the only ones, right? That's the problem. We all act like we're the only ones in your lives, but we're not. Yeah, that's how it is. But you can do it. You can do it. That's why you're here. Okay, so what was I talking about? Oh yeah, we're gonna start chapter 5 today. Chapter 5 is on clustering, and clustering is one of those topics that we typically don't cover in an introductory stats course, because it is more of a data science thing, and it is, you know, relatively new with computers and computing power being so available now. So it's relatively new. If you have any more questions about the assignment, let me know. Otherwise, we'll start chapter 5. Okay. We'll start chapter 5 then. So, I couldn't get away from, there's a lot of text here, obviously, and we're just going to talk about this text. Now, the problem is that this is all fine and good. We can talk about this theory, but we need to be able to apply it. But it's kind of like you have to read the instruction manual to use a power tool before you use it. In fact, well, you should, right? And so we need to have some idea of what we're asking R to do before we go ahead and learn how to do it, right? And so I know that students don't like doing this type of stuff. They don't like learning theory. What's the point? How am I supposed to know how to do it? Well, we have to start somewhere, right? And so here, the boring part is reading the instruction manual, and then we'll see how far we get today, either Friday or Monday. Then I'll show you some of the things that we've learned. How do we use them in R? How do we apply them in R? Okay, so we will get there. But first we have to kind of learn the rules and basically read the instruction manual, right? So first things first, chapter 5 is on descriptive data mining. Okay, I'm going to copy this whole chunk in. Okay. I'm going to redefine. So an observation or a record is going to be considered a row in a data set, right? So typically we would see it as a spreadsheet, and we would have an observation as a row and then a variable as a column. Okay, and so there's kind of examples here, but we have a pretty good understanding of, an observation. And in fact, I'm going to do it like this. Observation 1, 2, 3, blah, blah, blah. Variable 1, variable 2. Okay, just as a reminder that the rows are the observations and the variables are the columns. Okay, and so what's in here can be tons of things, right? And so that's what we're going to talk about, is one way that we could describe what's happening here. And so in this chapter, we're going to focus on descriptive data mining methods, which is also called unsupervised learning techniques. Okay, so in an unsupervised learning application, there's no outcome variable. Okay, so we're not predicting anything. The goal is just to identify relationships between observations. I almost said variables. Observations, right? So here, there's no outcome variable to predict. We're just looking at relationships between observations. Okay, if we think about these as customer 1, customer 2, customer 3, right? Then we could group them in different ways. Remember, so clusters are just groups, right? And so we can group different customers into clusters. Okay. So if the observations are customers, right? Especially in business, observations might be customers. It might be different branches of your business. It can be anything. So if the observations are customers, then we're going to try to figure out appropriate groups, right? Or clusters. We want to develop groups or clusters of customers. Okay. So that's what we're going to be talking about when we talk about clustering. Okay, so clusters are just groups, and so that's what we're doing. Okay, you might remember from things like maybe your intro stats course, if you did regression, right? Linear regression, you have some variable that you're trying to predict. We're not even doing that. We're just trying to figure out. So we're not saying, okay, this group boosts this prediction by this much. No, not yet. We're just saying, okay, we want to develop some method where we can put customers into different clusters, or in general, observations into different clusters. Okay, so what can we do? There are kind of two main ways that we can develop clusters. Okay. So there are two main ways to develop clusters. Okay. The first one is just randomly assign all your observations to some number of clusters, and then readjust the clusters until you have everyone in similar groups, right? Until you have these kind of homogeneous groups. Okay? And so all observations start in random groups. And are then redistributed, right, to more similar observation, or groups of more similar observations, and are then redistributed to groups with similar observations. Depends on what we're talking about, right? So we're going to have to figure out, okay, similar in what sense, right? Maybe it's income bracket, maybe it's gender, maybe it's, you know, they all bought milk on the same day, right? It could be anything. You know? So the second way that we could do is, so this first way, how I think of it, is you kind of start here and everyone's already in groups. And then you rearrange those groups, blah, 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 right? And we'll talk about how can you rearrange those groups, okay? The other way is everyone just starts as their own group, okay? And then from there, right, the similar groups get absorbed into each other, and then you end up with some number of groups. Okay? So all observations start as their own cluster, then similar observations are put into the same cluster, or then similar observations are merged into the same cluster. Yeah. Good. So in general, right, these are our two options, okay? And I think if you kind of, I don't know, had a bunch of Skittles and I asked you to arrange them into clusters, right? There are some obvious ways that you could arrange them, probably by color, maybe by size, I don't know. Right, and so there are kind of two ways that you could do it. I think for us, intuitively, we would start with the second one, right? We would consider everything their own unique thing, and then you would merge similar things into the same cluster until you don't feel comfortable merging two big clusters. Okay. This one is a little bit less computationally intense, okay, because all of them start in groups and then we can make adjustments. Right? So let's talk about how do we decide what goes where. So when we talk about cluster analysis, the goal of clustering is, of course, to organize observations into similar groups based on the observed variables. So it depends on, the type of variable that we have, which we'll see. So how we treat numerical variables versus how we treat categorical variables, that's going to be different. So it depends on what you want to base your clustering on off of. Okay. So clustering, we use clustering for, different reasons, but usually what we want to do is if you have a large data analysis project, then we can use clusterings to kind of reduce the number of situations that we need to consider. Okay, and so in marketing, we can divide consumers into different homogeneous groups, which is called market segmentation, right? And so we might have something kind of basic like females in the age group of 25 to 30, right? They like to buy this product, right? And so that's who we're marketing to. That would be something. How do we know that they like to buy that product? Well, from data. Right, we can't just assume that that's how it is. We'd have to look at data and actually see that, okay, that portion of the market or that segment of the market, they're the ones buying this product. Okay. I'm thinking about when I go to the grocery store, I'm probably in like the 40 plus women over 40 category. I don't know, pretty boring. Right? You can just think about when you go to the grocery store, what are some of the things that make your category, right? What are some of the things that you buy? Right? Just things that we can think about, right? Kind of pull a fast one on all these reward programs because they're keeping track of what we're buying, and they usually have a hold on our ages and our genders and whatever, where we live. Our only goal is to confuse the market researchers, right? You want to buy weird stuff like Ovaltine, and I don't even know what that is. Vegemite. I probably do. I love pickled herring. So that probably throws them off a bit. But yeah, keep them on their toes, right? Buck the segmentation. Anyways, right. And so if we have a cluster that we know exists, and that makes it easier to market to that group, right? And so cluster analysis can be used to identify outliers, right? And so maybe we're the outliers. Yeah. Right. And so if we're in a manufacturing setting, right, we might have quality control problems if we come across an outlier. So that would be a concern, right? If we're looking at financial transactions, then if we come across an outlier, so something, an outlier in this case would be, we expect them to be in a certain cluster, but they're not, right? So what happened? Why aren't they? Well, that might be because of fraudulent activity. Okay. Something to investigate, right? And so, okay, good. Maybe I'll say here, right? Outliers would be observations that are expected to be in one cluster, but end up in another. So outliers would be observations that are expected to be in one cluster, but end up in a different cluster. Okay. Good. So there are lots and lots and lots of ways that we can develop clusters. Okay, and so you know, we're going to talk about the key ones. But for example, first thing we would do, right? How do I decide what goes in a cluster? Right? How do I decide that that this consumer should be in this group and this consumer should be in that group? Well, it's not always going to be based off of categorical variables. It's not usually explicit in the data based off of one variable. So we need to incorporate other variables. And so how do we do that? Well, we can measure distances. Okay, we can measure distances between observations, which seems weird, right? But if I go to the store and I'm buying basically the same stuff as another person, then we would be in the same cluster. How do we decide that we would be in the same cluster? Well, based off of the items that we bought, right? And so, or the differences in the items that we bought, potentially. Okay, and so we need some way to measure distance. How we measure distance is going to depend on if we have numerical data or if we have categorical data. So we're going to start with numerical data. And I've got a little introduction here. So here, right, our goal is to group observations into clusters such that observations within a cluster are similar. Okay, but that's not all, right? We also want observations in different clusters to be dissimilar, right? You don't want to have overlap. You don't want to have a cloudy cluster, because then those aren't clusters at all. You want to say that, oh yeah, this group, they're all the same. That's me and Andrea shopping, right? We're buying all these weird old person things. And then here's all everyone else. Everyone else is buying, I don't know, cool groceries. Who knows? Right. And so we want them to be different, right? So so that's kind of a dual goal, right? We want everyone in the cluster to be the same-ish, right? And we want the clusters themselves to be unique, right? Or relatively unique. Sometimes you might have to have clusters that are really close to each other. But anyways, so what we need explicit measurements of dissimilarity, right? Or conversely similarity, right? So here, depending on what you're talking about and maybe what's more important to the data that you're analyzing, and that totally depends on what you're analyzing. So that's why it feels really vague here. But some metrics track similarity between observations, okay? And so if we're tracking similarity, right, how similar is everyone in this cluster, right? Then we would want to maximize the similarity between the observations, right? Whereas other metrics, don't be afraid of the word metric. Metric is just kind of a generic term that we use for any calculation that you've done, okay? So if you're reporting a calculation that you've done based off of your data, that would be considered a metric. There are formal metrics, but in general, you can use the term metric just to describe any calculation that you've done. Okay, and so other metrics measure dissimilarity or the distance between observations. Right? So then what would we want to do? we'd want to minimize the distance between observations in a cluster, right? So we'd want to maximize the similarities or minimize the differences within the cluster. It depends on what we're dealing with. Okay. So when we're talking about, let's just go all the way here. You know what? Just this, because I want to insert a little explanation there. When observations include numerical variables, the Euclidean distance is a common method to measure dissimilarity between observations. So dissimilarity is how different are these two things. Okay. So if we have observations U and V, okay, each on Q variables, what I want to do is I just want to show you what this would look like in a spreadsheet, right? Because otherwise, when we read these formulas, it's really hard for us to make the connection by just reading these formulas. So I just want to show you what it would look like. You would have kind of your, oops, your observation, oops. Observation U and observation V. Okay. So in this case, we're just talking about two observations. How similar or dissimilar are these observations? Of course, we don't just have two observations in our data set. We have many, many observations, right? But we can reduce them to pairwise comparisons, right? And so just to start us off here, we're going to just look at two, and then we can make the extension to multiple observations. Okay, so then we might have variable 1, variable 2, variable 3, all the way up to variable Q, right? So we're talking about Q variables. How we're going to denote that is we're going to have U1, U2, U3, blah, 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 all the way up to UQ. U1, U2, U3, UQ. Okay. Then for V, we have V1, V2, V3, all the way up to VQ. Okay. So if we think about U1 versus V1, right, that would be the difference between U and V on variable 1. It gets pretty tricky when we start thinking about more than two variables. So we're going to reduce this scenario down to two variables, and then I'll give you the formula for as many variables as you want. But the extension is going to be pretty obvious when we see it in the two variable case. Okay. So the Euclidean distance, and now I'll grab everything. The Euclidean distance here is how we usually find distances. We kind of take the, how a bird flies, or what's it called, the bee line? Is it because it's how the bee would fly? I don't know. Things I think about. So anyways, doesn't matter. But so the Euclidean distance between U and V is going to be U1, V1. So the difference in variable 1 squared plus the difference in variable 2 squared, plus the difference in variable 3 squared, and up to variable q squared, right? Add all those up and then take the square root. Okay, so what does that look like? Well, if we focus on just 2 variables here, okay, so if we focus on the Euclidean distance for 2 observations consisting of 2 variables, so q is going to be 2. So now just imagine, okay, we've just got these this first 2 column situation. Okay, we've really reduced it, right? We have the formula for what we would do if we needed to find it for more variables, right? But it becomes really hard to visualize, right? And so we're going to focus on just a 2-dimensional graph. Okay, and so what it would look like, well, the Euclidean distance is going to be this distance, right? The distance essentially of the hypotenuse, if you imagine some right triangle here. Okay, and so that's the most common distance. And I'll show you another distance, but this one is the most common. Okay, so the Euclidean distance becomes smaller as a pair of observations become more similar, right? So as these points get closer together, and it doesn't matter how, it doesn't have to come down on this line, right? Here we can move in a circle around a point, right? And we can still find that distance just the same. And so the problem is that the Euclidean distance is highly influenced by the scale on which the variable is measured. Okay, so that can be a problem, which I'm going to highlight. So here we've got this generic first variable and the second variable. The problem is if we talk about age and income, those are not on the same scales, right? Age, we go maybe from 0 to, let's say, 100 and some odd, right? Income is going to be on a scale of, I don't know, in the tens of thousands to hundreds of thousands, maybe, if we're talking about annual income, right? So that scale is hugely different from the scale that age is on. Okay, and so here, the Euclidean distance, right, is going to be affected by the scale that the variables are measured, right? For example, if the first variable, right, so U1 and V1, U1, V1, if the first variable is age, right, then we might have a difference in age and we can square that, great. But then what if the second variable might be in income, right? So even if we reduced it to thousands of dollars, right, this distance would be a lot larger, right? But we might want to account for how much spread do we have in the incomes in general, right? And so that sounds familiar, right? That sounds like a standardized score, and it is. Okay, so therefore, it's common to standardize the units of each variable j and each observation u. Okay, and so when you're reading this, it's easy to get kind of you just keep reading, right? So it's common to standardize the units of each variable j, of each observation u, blah blah blah. But what I want you to do is you really have to read it, right? And so to standardize the units of each variable j, okay, and so here, each variable j, right, variable 1, variable 2, variable 3, each of these variables, we can calculate a mean and a standard deviation, right, of variable 1, variable 2, variable 3, variable 4, blah, 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 right? Any generic variable, okay? Because imagine we're going to have more than just 2 observations here, of course, but also we're also assuming that we only have numerical data, right? And that's when it makes sense to talk about the mean and the standard deviation, right? And so a lot is kind of getting baked in here, right? And so remember, we are talking about numerical data. So each variable will have a mean and a standard deviation. So each variable will have a mean and a standard deviation. Oops. Right, which you can find, but usually you don't have to do it. Right, there are packages that do this for you, so we don't have to do it, but we have to understand what it's doing and why it's doing it. Okay, and so each variable j, right, is going to have some mean and some standard deviation because it's numerical data. And for each observation u, we can standardize that observation, right? And so uj would be something like u3 minus the average of the third variable, variable 3, divided by the standard deviation of the third variable in that case, okay? And so here, what you might remember is that z is x minus mu over sigma, right? Or I can't remember if we used s. Now I'm drawing a blank. I feel like we did something slightly different, but maybe I shouldn't have this in there anyways. I wanted to do just the generic one of these, but maybe this is a better way to do it because off the top of my head, can't remember if we used S or sigma. So don't want to confuse you, so I'll hold off. But anyways, a Z-score is a standardization technique, right? Z-scores are useful for a number of things. They're useful for identifying outliers, right? We use Z-scores to find outliers, right? And it just brings everything down so that we can compare variables without any units, right? So it reduces the units. Okay, so the Euclidean distance is basically the hypotenuse, right? So kind of the B line, right? Whereas, and this one's pretty cute, it's called the Manhattan distance. The Manhattan distance, if we look at it here, the Manhattan distance is going to be just the distance if you had to walk. So if you imagine we're back to traveling and you're walking around in Manhattan and you have to get somewhere, the only way to get there is if you walk the city blocks, right? You can't just cross through a building. And so that's where the name comes from, is you have to walk the city blocks, and that's the distance, right? And so the Manhattan distance, I'll bring this in here. And I'll also grab that graphic. Okay. So the Manhattan distance is a dissimilarity measure, so really just measuring the distance, of course, but it's more robust to outliers than the Euclidean distance. Okay, and so the Manhattan distance is the absolute value of the distances between the observations for each variable, right? And so U1 minus V1, if we focus on just two variables and two observations, well, here in general, we've got Q variables. But if we focus here, right, we've got observation 1 has some combination of variable 1 and variable 2, U1 and U2, and we can map them, you know, on a grid because it's numerical data, right? And then we've got some second observation V, where we have the outcome or the variable 1 and variable 2 for that observation V, so V1 and V2, which again we can map on here because we have numerical data, right? And so then if we had to find the distance, these distances, right, how do I find the length of this horizontal distance? Well, that's the distance between U1 and V1, right? And then how do I find this vertical distance? Well, that's the difference between V2 and U2, right? Or U2 and V2. So that's where we have U1 minus V1. If I take the absolute value, it just takes that distance, right? And so the order that you subtract them doesn't matter, but as long as you're consistent, right? So U1 minus V1, take the absolute value, and then do it for the second variable, and then do it for the third variable, fourth variable, fifth variable, qth variable, but that becomes hard to visualize. So we stick, for the visualization, just to show you what's going on, we stick to 2 variables. Okay, and so the Manhattan distance between 2 observations is the sum of the lengths of the perpendicular line segments, right? And so here, the Euclidean distance is, I like to call it the B line, go straight there, whereas the Manhattan distance is if you traveled along city blocks. Okay, one thing that I will highlight as well is that the Manhattan distance is more robust to outliers than the Euclidean distance. Okay, you would still use the standardized scores. So it's not clear here, but we would still use the standardized scores even if you're finding the Manhattan distance. Okay. We should still use standardized scores for Manhattan distances. Okay. So that's not clear from the blurb here, but I'm saying it, so it's true. I guess not always the case. No, but in general. So in general, we're going to use standardized scores. Okay, and so just because you don't want to have to deal with units and you don't want to have to deal with kind of these absurd measurements, right? Like income, for example, if you're comparing it to age, it doesn't make sense. You can't compare those two things, right? But if you standardize them, then it's all of a sudden easier to compare them. I will mention that the textbook has a really good example that they work through the entire way through, but I opted out of that because it would have made the notes just the textbook, and that's not what I wanted. I just want to talk about the general ideas. But if you are kind of hungry for an example, like an actual example, then the textbook has one for you, okay, that they work through for all of these scenarios. Okay, so what we can do is once we've converted to z-scores, sorry, it's so slow today. So after conversion to z-scores, what we can do is, so we convert to z-scores so that we have comparable values, right? So everyone's on this standardized playing field, right? But after we've done that, okay, we could assign, so we, the analyst, could assign unequal weighting to variables, okay? So what you could do is you could assign weights to different variables. So for example, if you're talking about customer observations on income and age, for example, right? What you'd have to do is you would have to calculate the z-scores for each of those observations for each of those variables, right? So you're basically replicating your data set, but standardizing it, right? So then what you could do is you can, if you're talking about income, right, versus age, but maybe income is more important to you, right? You want to have rich clients, right? So you want to emphasize that more. Maybe you don't care about their age so much, right? Who can I get to here? And so what you could do is you could multiply those z-scores by 2 or some factor, right? If you want to treat the income with twice the importance of age, right? So that's just an example. But so what you can do, so it gets kind of backwards, right? So we standardize because it removes the bias, right? Due to kind of measurement and units and all that kind of fun stuff. Variability in your data, right? That's going to wreak havoc. Okay. And so standardizing removes the bias due to the difference in the measurement units. And then what we can do is then we can apply some bias. That seems weird, right? But you only do it if you want to emphasize something. If something is really important to you in your analyses, then you might assign a weighting to it. So, and variable weighting allows the analyst to introduce any desired bias based on the business context, right? And so here, that's kind of a weird thing to introduce, right? But once you think about the example of, okay, well, maybe I don't care so much about age, or maybe I can't control so much on age, but maybe I want to focus on the income category that they're in, then yeah, we would want to bias it that way, right? And so the key is that you want to remove some of the bias, but not all of it, right? And so you completely remove it by standardizing, and then you apply some bias potentially, but that's going to be based off of this very vague business context, right? And so that's not always obvious, but that's going to come with, talking to your colleagues, talking to your boss. Oh, we usually do this for these situations, right? And so you're not out there alone, right? There's going to be kind of whatever the business context is in your case, right? They're going to tell you what it is, and then you just do it. Yeah. Becomes a little bit trickier when we're talking about categorical variables. So remember, we've been focusing just on numerical data, right? Then we can standardize because we have a mean and we have a standard deviation, and we can look at the distances because in theory we could map all these variables, all these observations, and we could actually measure the distances. Becomes a little bit trickier, and I should say a lot trickier when we have categorical data, especially if we have dummy variables like 0, 1 data. So if I copy this whole thing, and I do want to separate these. Now consider categorical data. Specifically, categorical data that are dummy variables, so 0, 1. So here, variables encoded as 0, 1, so dummy variables. Okay. So now in your data set, what you have is you might still have observation U and observation V, right? And you might have Q variables, but now we're assuming that all those variables are going to be categorical, right? And so we might still have the same situation where we have the observation U and the observation V. And we have variable 1, variable 2, variable 3, all the way up to, and I think we can still call it variable Q, right? But the key is here that these are all dummy variables. Okay. So just as an example, right, variable 1 might be 0 if they're male and 1 if they're female, right? And so I might have something like, and I'm going to use a different color to show you that it, they're just dummy variables. And so I might have 1, 1, right? Both of these are female. Okay. Variable 2, did they shop on a Monday? Yes or no? Right. And so a lot of categorical data is not dummy variables to begin with, right? But we create these dummy variables, right? Did they shop on a Monday, a Tuesday, a Wednesday, a Thursday? And if they shopped on a Monday, then we give them a 1, right? And so maybe it's 1, 0. Variable 3, did they buy bread? Yes or no, right? And so dummy variables are really just yes, no situations. And so here, maybe neither of them bought bread. Okay. And so on and so forth. And here, maybe we have 0, 1. Okay. So just as an example of what would this data look like? Okay. So what we can do is we can look at how did these outcomes and how did these observations match, right? If they both have a 1 for variable 1, then they would be considered the same, right? And so that would generate a cluster, right? Whereas here, you've got a 1 and then a 0. So here that would indicate a difference, right? And so we can use these to find similarities or measure dissimilarities, if we want to talk about it that way. They're kind of the same, right? How similar are things or how dissimilar are two things? We do kind of the same thing. So here, one thing to remember is that a 1 in a dummy variable is going to be an explicit thing. It's going to be something that we can put our finger on and say, did they shop on a Monday? Yes or no, right? And so here, so let's say if variable 3 is 1 if they shopped on a Monday, 0 if they shopped on some other day, if they shopped on another day. One problem becomes these two zeros aren't necessarily the same. They don't mean the same thing. All they mean is these two people did not shop on a Monday, right? So here, these zeros might not mean the same thing. Oh, need a little bit more room here. Wink. Mean the same thing. Right? A zero, they could have shopped on a Tuesday, Wednesday, you get the idea, right? And so all we know is that they did not shop on a Monday. So then we start questioning, well, how can I decide what a good one would be? And that's going to be kind of depending on your data, right? And depending on what you want to analyze. So you want to make sure that if you have dummy variables, you want to make sure that your one is the most important characteristic that you're trying to tease out, right? And so if you are constructing dummy variables, you need to be really careful in picking what the one outcome is, right? Because everything else is going to get lumped into a zero. And you need to be very careful selecting the outcome that will represent a one since all other categories or all other outcomes will be grouped as zero, right? So then you'll lose that information. Since all other outcomes will be lumped into zero. Okay. So one of the ways that we can do this, and you're not obviously going to have to do this by hand, but we do need to understand what R is doing when we ask it to do something. Okay, and so I'm going to talk about it and just kind of hopefully sell you on it. It makes sense, right? But what we can do is, well, how similar are observations U and V? The most obvious thing that we can think of is the matching coefficient. So the matching coefficient is going to be the number of variables, right? So the number of columns with matching values for observations U and V over the total number of variables. Okay, so if we go to our example, right, this variable 1 would be matching, variable 2 is not matching, variable 3 is matching, right, because they're both zeros. Now we're going to have ways to deal with that because we just talked about, okay, just because they're zeros doesn't mean that they're necessarily the same, right? It just means that they're not ones, right? And so, but they're still similar. Okay, so they still have the same outcome. And then I don't know what happened here, but let's, if we focus on just these first 3 variables, right, then we have 2 that were similar out of a total of 3 variables. Okay, so then our matching coefficient here would be 2 divided by 3. Okay. So what we can do is we can talk about, we can subtract the matching coefficient from 1. Okay, because this is going to be a fraction, right? And so it's going to be a proportion between 0 and 1. So we can subtract it from 1. 1 would be if 3 out of 3, right, had the same, if all 3 matched, right? And so we can talk about the matching distance between U and V, right? Where we take, and we've got some notation here, the distance between U and V and the matching distance is 1 minus the matching coefficient. which once we kind of remember, okay, I need to have a common denominator in order to subtract fractions, right? Because the matching coefficient is a fraction. I can figure this out as the total number of variables minus the number of variables with matching values, which translates to the number of variables with mismatching values over the total number of variables, right? So now I've got that common denominator. So that's going to be the matching distance. So in this case, right, if we just focus on these first three variables, the number of variables with mismatching values is going to be 1, right? Because variable 1 and variable 3, those are matching for U and V, right? And so variable 2 is the only one with mismatching values. So that's going to be 1 divided by, we're looking at 3 variables, right? And so that would be the distance, the matching distance between U and V. Okay, so good. We're going to talk more about how do we deal with dummy variables. And let me just see if there was some last minute. No. So you can read. No, I'll read it to you next day. But if you want to have a heads up of where we're going with this, on Friday, we're going to talk about Jacquard distance, and then we'll get into some different methods of clustering. But we already talked about in general what those different methods are. Okay, pretty sure I'm out of time. If you have any questions, let me know. Otherwise, do your best on the assignment. And remember, I'm going to go easy on you, so don't worry about that, but give me your best shot. And good luck, and I'll see you Friday. I'll stop this.